But anyway, we were clearly seeing seasonal variations there. Okay, so when we see variations in the poles, like I was just talking about carbon dioxide, well, if we're able to thaw carbon dioxide, now carbon dioxide doesn't exist in any liquid form on Mars. It turns out with the very low pressure that we have on Mars, what actually happens is the carbon dioxide, when it melts out of the polar regions, it sublimates. If you remember what that is, it sublimates. It goes straight from the frozen state to the gas state. So that variation we saw in the polar amount of carbon dioxide is actually going to lead to changes in the atmosphere, because you're putting that carbon dioxide into the atmosphere. So we'll talk about that a little bit now. Well, back in the mid-1970s, when all of you were watching Barney version 1.1, the original version of Barney, actually in test market back in the 1970s, that was actually our first opportunity to measure the daily variations of temperature on Mars. You really can't do that too effectively from Earth because of the large distance and the inability to really resolve different areas on the surface. But when we landed a lander on Mars in the mid-70s, actually 1976, U.S. bicentennial, we were able to actually measure the variation, and we were able to see the atmosphere. There actually is sort of a little bit of a pinkish atmosphere. And the Viking 1 lander measured these variations, this is in Celsius, these variations, and the variations you're seeing, the spikes up and down, are daily variations. And you can actually see Martian days indicated down here. So what we're seeing, and remember 0 Celsius is the freezing point, so it's mighty cold even at high noon. At high noon, it's still around -30 centigrade. Okay, pretty darn chilly. And then at night, you're talking more than -80 Celsius. So again, although sometimes people think of Mars as being sort of similar to Earth somehow, it's really not very similar to Earth in almost any way that you can think of. And this is one example. It's much colder. It's a much colder planet. And in fact, these temperatures are the reasons that we're seeing so much of that frozen material at the poles. It's also our first kind of evidence for the fact that Mars isn't in the habitable zone. I mean, remember, the habitable zone is the zone where we're going to get liquid water. You're never, ever going to get liquid water with these types of temperature variations. You're never warmer than -30 Celsius. You know, it's much, much too cold to have liquid water. Okay, so there is a thin atmosphere and this low variable temperature. When we look at the limb of the planet, for example, here from orbit, again, we call it the limb of the planet. It's kind of the edge of the planet when you look at it. But you're going to look through the thickest layer of atmosphere when you look at the edge of the planet, just like when we look at sunset on Earth. You see the reddish sun. You look at the thickest layer of atmosphere, much thicker than if you just look up. Okay, so we're seeing the clearest evidence for a Martian atmosphere when we look at the limb of the planet. You can just see that little bit of haze there. Okay, so let's talk about Mars's atmosphere now. As you are familiar with, we always plot these temperature curves, which can be read to determine temperature and pressure, right? Depending on the way that we look off the curve. If we look down, we see a temperature scale. If we look to the right, we see a pressure scale. And remember, these units are Earth atmosphere units, just like when we looked at Venus, for example. And then we have altitude over here. So 0 altitude is the surface temperature 250 kelvins, roughly about 100 kelvins colder than Earth's surface temperature. So mighty cold. 273 kelvins is 0 Celsius freezing point. So even at the surface where it's the warmest, it's still, 25 or so degrees below freezing, just like we saw in the last plot of the Viking temperature variation. Okay, so it's cold. And it gets even colder when you go up. Eventually the curve turns around and we get a rise in temperature because you're becoming exposed to solar high energy radiation, which tends to heat things up in space a bit. Now, when we look at the pressure, we see a surprise. Remember when we looked, well, if we were looking at an earthly curve here, this would be a 1 at the bottom because it would be 1 unit of Earth's atmospheric pressure at the surface. When we looked at Venus, we saw a 90 down there, 90 times Earth's atmospheric pressure at the surface of Venus. Now we look at this and we see just the opposite, only 0.6% of Earth's surface pressure is the pressure at the surface of Mars. So this is our first indication that this is a very, very thin atmosphere. It's not a vacuum, by earthly standards. It's not a vacuum, but it's a mighty thin atmosphere, only 0.6% of the pressure of Earth's atmosphere. we do see water ice clouds and carbon dioxide ice clouds. Now this actually is kind of interesting thing right here, this offset. Because remember I just made the point that carbon dioxide freezes at a lower temperature than water ice, right? And you can actually kind of make sense of that if you look at this temperature curve and these altitudes. The water ice clouds are down in an area where it's certainly below freezing for water ice. But the carbon dioxide clouds don't form until you get up to around 50 kilometers because you need to get this lower temperature, like about 150 kelvins, to get that formation of frozen carbon dioxide. Oh, just one other thing I can say. The pinkish color of the atmosphere is because we have Martian dust storms which whip up that reddish dust on the surface of Mars, which is reddish because of the presence of iron oxide. Remember, it's a reddish-looking desert surface, kind of like around Albuquerque or something like that. And when you get a windstorm, which you do get, even in these low pressures, then you're whipping some of that dust into the atmosphere, and that gives it this pinkish hue, which we actually saw right there. This pinkish kind of haze is actually the color of the true Martian atmosphere. All right, so now we're going to look at atmospheric composition. All right, so if we look at a percentage basis, we see that Mars' atmosphere is about 95.3% carbon dioxide. There's actually a little bit of water vapor. Not too surprising because there is a freeze-thaw cycle to some extent on Mars, so there's going to be some water vapor. There's a little bit of free oxygen, and the reactivity of the free oxygen is what actually gives you that iron oxide, the reddish color. Some trace gases here. Now when we contrast this with Venus, now if you just look at the top line, you might be led to the conclusion that these atmospheres are somehow similar to each other because they're both about the same percentage of carbon dioxide. But the thing you got to keep in mind is that Venus, with that 90 times Earth's pressure at the surface, versus only about 1% of Earth's pressure from Mars, what that means if you do the math, Venus's atmosphere is about 10,000 times thicker, more dense than the Martian atmosphere. So even though they both have similar percentages of carbon dioxide, the actual amount of carbon dioxide, if you look at the tons of carbon dioxide in the atmosphere, Venus is far, far higher, like 10,000 times higher, because that density is so much higher. Now, when we move past the carbon dioxide, then we see really no similarity between the two atmospheres. Venus has practically no free oxygen or water, a little bit of nitrogen. The nitrogen percentages are kind of similar, but we don't see, on Mars we see water ice clouds and carbon dioxide clouds. The clouds on Venus are sulfuric acid clouds. So again, you kind of get the feeling that you're looking at objects that might have started out pretty similar, but took radically different evolutionary paths, basically because of the distance that they are from the sun. So here I make this point that, again, the 10,000 number for the density of Venus versus the density of Martian atmosphere. And of course, we have a tremendous difference in the temperature, like a full factor of 3 difference in the Martian temperature and the Venusian temperature. And Earth is somewhere in between. So just a couple of photos here that show the freeze-thaw cycle on Mars, kind of frozen frost form. And certain craters, low-lying craters, you can see low-lying mist and frozen vapor, which would kind of burn off, as we say, just melt when the sun comes up. Here's a photo where you can see these wispy, frosty areas during winter in the southern hemisphere. And again, there's definitely some sort of atmospheric variation on Mars. Okay, so we'll talk a little bit more about the Martian atmosphere when we talk about the formation of the Martian atmosphere. We didn't talk about that yet. We only talked about what the Martian atmosphere looks like right now. But of course, there's a history that brings us to that current Martian atmosphere, so we'll get back to that. But water on Mars, we've already seen there's abundant evidence for that. We see things like this, craters that have been formed by impacts, but then serve as sort of a little bit of a barrier to water flow, giving us these island-type formations. And other areas where we see evidence that craters look kind of splooshy, as we say in the field. It looks kind of like there was frozen content there that got manned by a large rock. And you can kind of see some, if you can see this clearly, there's a little bit of splooshiness around there. Well, when we start looking at the geological evidence, the kinds of rocks that are accumulated at different landing sites where we've landed. The fact that we're seeing an accumulation of rocks from different parts of the southern hemisphere of Mars all together in this mid-latitude region near the equator is part of the evidence that we have for this huge flood in the distant past. We're talking billions of years ago. And it would have been just an incredible flow rate, like 100 Amazon rivers running basically from the southern hemisphere to the northern hemisphere. Well, where is the water now? Remember, in the case of Venus, we had this idea of a runaway greenhouse effect, where we had so much heating because of the greenhouse effect on Venus that the H2O went high in the atmosphere and was split up by solar radiation, and then you have oxygen and hydrogen running around, and the hydrogen leaves on Venus, right? So we have chemical evolution on Venus, which leaves us with an irreversible situation. So that's why we call it, the Venus case, a runaway greenhouse effect. Well, on Mars, it's a little bit different, because what happens is the water actually is still there. There was never any chemical process we know of that would have split the water off. We didn't lose the hydrogen or anything like that. So we think that the water that participated in this incredible flow is probably actually there, for the most part, in the northern hemisphere, frozen as permafrost below the surface. So again, just a topological map where you can see the landing zones where we've landed, and the rationale, again, for those landing zones is that we want to land where it's relatively smooth, just like on the Mariana moon, but you want to be close to this division with the southern hemisphere so you can explore as much of the geology as you can. And over here we're seeing the Tharsis Plateau region. A general uplift right there. There's the Valmont and Aris, that big tectonic crack right there, and these large volcanoes, Olympus, Mars, and the others. So this is actually kind of the best view we've had of that Tharsis region, where you can see the Mariner Valley and the shield volcanoes. Another close-up of some water-resistant feature. It goes on and on. There's thousands or even millions of snapshots of Mars that reveal evidence for very strong flow in the past. Things that look like river deltas and river systems on Earth abound on Mars. For instance, this is actually I think this actually is a river on Earth, that we're seeing right there. And this is a similar feature on Mars. A characteristic serpentine kind of path that happens when water flows due to the instability of the silt that moves along. So if we compare these, they look extremely similar to each other. So there's certainly evidence for these ancient riverbeds on Mars. Now this is evidence, again, for a massive flow region where the ground is excoriated by debris that's carried by water, just like we would see on Earth. And again, a close-up of a splooshy kind of area where you get the impression that this was kind of a frozen surface area, probably frozen tundra type material, which got whammed by a big impact crater from an asteroid, and we had these waves of material that kind of flowed out from that area.